Welcome back. Today we're hitting section 8.1 on basic integration rules. That is the author's choice of words, not mine, to call this basic. Some of them, yes, some of them not so much basic. So I do want to kind of go through a few of the basic integration rules. On page 522, there's a list of 20 of the basic integration rules. The simpler ones we're going to skip over. We're just going to look at a few of the more intricate ones. So we'll start with y is a to the x, and we'll look at why the integration works kind of the way it works. So if I take the natural log of both sides, natural log of y is natural log of a to the x. Properties of logarithm, I can now write this as natural log of y is x natural log of a. And if we differentiate both sides with respect to x, derivative of y is 1 over y times dy dx. And derivative of, this is now a linear, natural log of a is just a constant. So a here we're assuming is positive and not worth 1. So x times a constant is just a linear, derivative of a linear is the coefficient. So then dy dx is y natural log of a. So dy dx then is a to the x natural log of a. What does that do for us? Well, that gets us to looking at integral of a to the x dx. We'd like to see a natural log in there. We don't have it, so we can multiply by 1. So that's 1 over natural log of a, excuse me, times a to the x. And since we're looking at an indefinite integral, we'll go ahead and toss a plus c in there. So we'll just derive a couple of these. The tangent integral of tangent x dx. If we just split it into sines and cosines, it's a little easier to see what's going on. So here we would let u equal cosine x, which would mean du is minus sine x times dx. Again, we'll use a little multiplication by 1. I see a sine x dx. I don't see the minus sign there. So multiply by -1 inside and out. Multiply by something worth 1. So we have integral opposite of the integral of u to the -1st times du. So that should look familiar. That's natural log territory. So opposite of natural log of absolute value of u plus c, and a little bit of back substitution. U we said was cosine x. Cotangent you can work in a similar manner. In fact, let me just have you start it. Go ahead and pause the video, see if you can derive it. Okay, welcome back. Again, sines and cosines. So cotangent is the reciprocal of tangent, so cosine x over sine x times dx. So here u is then sine x. Du would then be cosine x dx. So that one we've already got what we're looking for as far as du. So this would be the integral of u to the negative first times du, which is natural log absolute value of u, and a little substitution, natural log of sine x plus some arbitrary constant. So hopefully you're able to derive those pretty similar to the last one. We'll take a look at the secant one together. We had that on our quiz and it was just a given. Let's actually see where it came from. On this one, there's a little bit of a mathematical sleight of hand happening. We're going to multiply by 1 again, but in a way that's sort of convenient for this problem. So we're going to multiply by secant x plus tangent x, top and bottom. So then we have integral of distributing secant squared x plus secant x tangent x all over secant x plus tangent x. And we're multiplying that fraction by dx. So here we can let u be secant x plus tangent x. Derivative of secant is the secant tangent. Derivative of tangent, hopefully you remember, is secant squared. And of course we would multiply that guy by dx. So then this is now of the form integral of du over u, which is natural log absolute value of u plus c. And then a little back substitution, natural log absolute value of secant x plus tan x. Close it on up, plus c. So cosecant can be found in a similar manner. I'll just give you a hint on that one. We won't run through the whole thing. So there, your version of 1 would be cosecant x plus cotangent x, top and bottom. It's a little hint to get you started on that one. For the 14th one they have in the list in your book, derivative of tangent x, again, hopefully you remember, is secant squared x. So then the antiderivative of secant squared x dx would be tan x plus c. So we can do a similar one for cosecant squared. Similar for integral of secant tangent, etc. So you can look at some of those and just sort of use your derivatives to make sure you can work back and forth between the two. Some of the inverse trig, I want to at least walk you through what we're looking at. So if we let sine, my apologies, a step ahead there. Let y equal arc sine of x divided by a. We can use a little bit of trig on that to develop a new integral. So if y is an arc sine, then sine of y is our argument x over a. And we can differentiate both of these with respect to x. So y is defined implicitly in terms of x. Actually, in that first step, it's explicitly defined. So derivative of sine is cosine, so we have cosine y times dy dx. Right hand side is now just a linear, so a derivative would be 1 over a. So then dy dx is 1 over a cosine y. So here's where we can have a little drawing sort of help us out. So the angle in question was a y. Sine of y, sine, remember, is opposite over hypotenuse. So x over a, so that makes this other guy, by the Pythagorean theorem, square root of a squared minus x squared. Leg squared plus leg squared is hypotenuse squared. So then the cosine of y by our drawing, cosine is adjacent over hypotenuse. So we have 1 over a times cosine of y is square root of a squared minus x squared over a. And notice the a over a will drop out. So 1 over square root of a squared minus x squared. So that's our derivative. So if we look to hit the reverse gear on that and do an antiderivative of something of the form integral of 1 over square root of a squared minus x squared times dx, we know that that would then be arcsine of x over a. So if we know that this is the derivative, we know the original is our antiderivative, and of course we'll add our arbitrary constant plus c. Make sure that was low down enough on that previous one, so if you're missing anything, now's your chance to pause it. Okay. We'll play with another one of these. This time we're going to let y equal 1 over a arctangent of x divided by a. So we'll start this one together. AY is then the arctangent of x over a. So then the tangent of AY is worth x divided by a. So go ahead and see if you can differentiate both sides of this and solve for dy. Give it a pause and come on back when you're done. Okay, so differentiating both sides of this with respect to x. Derivative of tangent, remember, is secant squared. We also have a constant a in there, so that's our chain rule happening there, and times dy dx, since y was in this form implicitly defined in terms of x. Derivative of x over a, of course, is still 1 over a. All right, so we have a. Secant is, remember, 1 over cosine. So a over cosine squared of ay times dy dx is 1 over a. So multiply both sides by the reciprocal. The a's are going to drop. So dy dx is equal to cosine squared of ay. And then we have a squared downstairs. So when we hit the reciprocal on both sides. Okay, so here is where you hopefully think to make a quick little sketch of a triangle here. So our angle here will go back to the tangent y. So y is our ay, my apologies. Ay is our angle, tangent of ay. Tangent, remember, is sine over cosine or opposite over adjacent, making this guy square root of a squared plus x squared by the Pythagorean theorem. So by our drawing, the cosine of ay would be adjacent over hypotenuse. So then the cosine squared of ay is then just a squared over a squared plus x squared.